Welcome back to Honors Calculus. In this video, we're going to be looking at one-sided limits. As we've discussed in the last few videos talking about the idea of limits, our goal is to try to find a way to establish a concrete definition for when a function is and is not continuous. The limit that we've defined works very nicely as a way of looking at a function that is continuous. And so what we want to look at continuing onward is that other case of the limit does not exist. And the one-sided limit is going to be one of the tools that gets us there. So if I get my head out of the way here, and quickly sketch out the definition of a limit that we've talked about. The limit as x approaches c of f of x is equal to L if and only if for every epsilon greater than 0 there exists a delta greater than 0 such that f of x minus L is less than epsilon whenever x minus c is between 0 and delta. A one-sided limit is going to be written as the limit as x approaches c with a superscript plus, and we're going to read this as the limit as x approaches c from the right of f of x is equal to L if and only if for any epsilon greater than 0 there exists a delta greater than 0 such that the absolute value of f of x minus L is less than epsilon whenever, and we'll drop the absolute value bars and say 0 is less than x minus c is less than delta. And limit from the right is one side, the other side would be the left, and we will establish that much the same. The limit as x approaches c with a superscript minus, which we'll read as approaches c from the left, of f of x is equal to L if and only if for all epsilon greater than 0 there exists, that's not an e, there exists a delta greater than 0 such that the absolute value of f of x minus L is less than epsilon whenever, all right. Now, if x is to the right of c, that means that x minus c is going to be a positive number. If x is to the left of c, that means that x minus c is going to be a negative number, which is why we'll get the negative of delta less than x minus c less than 0. All right, so we have a one-sided limit on the left, we have a one-sided limit on the right, and the definitions look incredibly similar to the definition of the function. And so just like the original definition of a limit, I want to think about this graphically before anything else. So let's take a look at something that looks like that. And all right, here is our limit point. When we are looking at the limit from the right, we are saying take a delta, but only take it on that side. When we're taking the limit on the left, we're saying take delta only on this side and look for that window. And so the first thing I'm going to do, I'm going to label this as a corollary. Technically, it shouldn't be a corollary because we don't have a theorem. But my corollary is that the limit as x approaches c of f of x is equal to L if and only if the limit as x approaches c from the right and the limit as x approaches c from the left are both equal to each other and are both equal to L. And the proof of this is very simply looking at this inequality. If x minus c is between 0 and delta, that means that the absolute value of x minus c is between 0 and delta. And if x minus c is between negative delta and 0, then the absolute value of x minus c is between 0 and delta. But this is what it's all about. We can take our idea of a limit and we can trace one half of the curve. And we can trace the other half of the curve. And we can make sure that they agree and they meet in the middle. For functions like the ones we were talking about in the last few videos, where the function is going to be continuous and everything is going to be well behaved, this is not a concern. This is not something that we run into as a problem. This becomes a point of interest as a way of showing that a limit does not exist. So looking at one-sided limits that do exist is not generally interesting. It's worth doing, and we'll see a couple of cases where it is worth doing, but by and large, we look at one-sided limits in cases where we are either concerned or even certain that the limit won't exist at all, and we use the one-sided limit as a way to show that the limit does not exist. And the classic example of where a one-sided limit is useful is in a piecewise defined function. Absolute value, sure, but really any function will work. So let's consider the function f of x equals x if x is less than, let's make that strictly less than 0, and f of x is equal to x squared if x is greater than or equal to 0. I can sketch this graph. I can sketch it by hand to get enough information. You could use Desmos or something like that in order to graph this. But the graph of y equals x looks something like that. The graph of y equals x squared looks something like that. There's a point in the middle where these two do in fact match up, but it's a point of interest because the name of the function has broken up, or the definition of the function. So if I want to take the limit of this function at that point where things are changing, I should look at it as a one-sided limit. I should look separately at the limit as x approaches 0 from the left of f of x, and I should look at the limit as x approaches 0 from the right of f of x. In our definition of the one-sided limit, as x approaches 0 from the left, that means that x minus 0 is between negative delta and 0. It's less than 0. And whenever x is less than 0, this function has a definition of x. So we're looking at the limit as x approaches 0 from the left of x. And we know how to deal with the limit of x approaches anything of x. It just gives you that thing. On the other side, when we approach from the right, approaching from the right is defined as coming through from the positive values. right? 0 is less than x minus c is less than delta. And in the positive values, our function is defined as x squared. And we know how to take the limit on x squared. It's just going to be c squared. So in this case, 0 squared, which is 0. Right? And these agree. So the limit as x approaches 0 of this function is in fact equal to 0. As another example, let's take a look at the piecewise defined function g of x, which is defined so that g of x is equal to 0 if x is less than 5, and 1/2 of x minus 1 if x is greater than or equal to 5. Once again, you could use computer software to graph this function if you wanted to, but it's a relatively simple function. So I can just sketch the graph by hand. All right, here's 5 over here somewhere. And so we are less than 5 looks like that. 1/2 of x minus 1. Let's see, when x is 5, x minus 1 is 4, half of 4 is 2, which will be a point right there, and slope of 1/2, which kind of does something like that. And we can see here that this function has a jump discontinuity. It moves from this to that without hitting any of the stuff in between. So we know that the limit should be ill-behaved at this point. But we can verify that by analyzing the limit as x approaches 5 of g of x. And again, because this is a piecewise defined function, it has two different values near 5. That's where it jumps from one to the other. That's how you know that you should analyze this by looking at one-sided limits. The limit as x approaches 5 from the left of g of x, and the limit as x approaches 5 from the right of g of x. And whenever we are looking to the left of x equals 5, we are looking at the branch that says 0. And the limit on 0 is just definitely always going to be 0. Whenever we're looking to the right, we are looking at the branch that says 1/2 of x minus 1. And we know we can split this up. We can evaluate at that just by distributing and then using linearity. We're going to get 1/2 times 5 minus 1, which is 1/2 times 4, which is 2. Because the one-sided limits do not agree, this limit does not exist. Right? Because the one-sided limits disagree, the limit as x approaches 5 of g of x does not exist. All right. One more example for you. Let's take a look at h of x, which is a piecewise defined function. This time is going to be defined using three pieces. So h of x is equal to x if x is less than 1. H of x is equal to 0 if x is equal to 1. And h of x is equal to x squared if x is greater than 1. All right, we have a piecewise defined function with three pieces. Let's go ahead. I've been at this long enough. Let's go ahead and jump over to Desmos. There we go. So that I can show you how to graph a piecewise defined function in Desmos. The process is fairly straightforward. Piecewise defined functions start with a curly brace. We start our graph here with a curly brace. The one thing that's challenging about it is that you actually have to set up the definition backwards. So the range is x less than 1. We put in a colon. We put in the name of the function. In this case, when x is less than 1, we get x. Then we put in x equals 1. We put in a colon, and we get 0. Then we put in the next range, which was x greater than 1. We put in a colon, and the function there was x squared. And we should put a curly brace in at the end to see how this all works out. All right. And it's very difficult to see. I kind of have to hover over it to make it show up. But we can see that this function has a discontinuity. If you have studied discontinuities before, you've learned that this is called a removable discontinuity, where there is one point that jumps away from the rest of the line. But it is a discontinuity. So it could end up that we have some trouble with the limits. But let's go back to the notes and see how it actually works out. We're going to be taking the limit as x approaches 1 of h of x, and we're going to do that by analyzing each piece in turn. We'll take the limit as x approaches 1 from the left of h of x. And whenever we're to the left of 1, we're in this regime where we are taking the limit on x. And the limit as x approaches 1 of x is 1. Then we'll take the limit as x approaches 1 from the right of h of x. And whenever we are to the right of 1, we're in this regime where h of x is x squared. And so we get 1 squared, which is 1. The results agree. We get the same thing on the left and on the right. So in this case, even though we know from graphing it that there is a discontinuity, it's a hidden discontinuity. It's one that Desmos doesn't even show, but we know it's there. We know that this graph does a thing like that and has a jump right in the middle of it. So this has a discontinuity, but the limit still exists. Now, the limit came out as 1, and if we tried evaluating this function, do notice that h of 1 is equal to 0. So that's a nice sign that something is still going a little bit weird. The limit exists, but it didn't come out to what the value of the function actually is. So this function is still doing something a little bit stranger than the functions we were looking at in earlier videos. Later on, we are going to define continuity and find a clear way of looking at this as one of the special cases. But that's for a future video. For right now, I've got one last piecewise defined function, and this is one for you to take a look at. Let's take a look at the piecewise defined function defined so that f of x is equal to 5 minus 3x if x is less than 1. I'm sorry. Yeah, we'll go with that. 5 minus 3x if x is less than 1. And 1/2 of x squared plus 3 if x is greater than or equal to 1. And I would like you to evaluate the limit as x approaches 1 of this piecewise function. All right, see what you can do with that one, and I'll see you in the next video.